I plan to spend the next few lectures talking about cosmology. Cosmology, of course, is the study of the universe as a whole on the largest length scales. And the starting point for this study is the observation that the universe is isotropic. This means when we look out beyond the nearby planets, beyond the Milky Way galaxy, beyond our local cluster of galaxies to the largest length scales, we find that the universe looks the same in all directions. So this observed isotropy occurs at length scales of clusters of galaxies. So greater than about 10 megaparsecs. And we observe this isotropy whether we look at the visible light or X-rays or in any other wavelengths. We also see that the universe is isotropic when we measure the microwave background radiation. The microwave background radiation is uniform in all directions to within about 1/1000th of a percent. And those tiny variations are understood to be a result of the fluctuations in the universe, in the early universe, that led to the local formation of structure. Local meaning on smaller length scales, the formation of galaxies and, of course, stars and planets and so forth. Of course, the observed isotropy of the universe is only from our own vantage point, so this is us here on Earth. Isotropy at a single point like this doesn't preclude the possibility that the universe consists of concentric shells, different layers of different density, different chemical composition, and so forth. So isotropy at a single point does not imply that the universe is homogeneous. Does not imply. But in fact, when we look out in any direction, we don't see different shells, different layers of different density and composition. What we see is pretty much the same density and same chemical composition as the universe around us. So we observe the universe to be not only isotropic but also homogeneous. So we observe the universe is homogeneous. Now, this is a fairly non-trivial assertion because keep in mind, as we look outward to the distant universe, we're also looking back in time. So if we look far enough out, we see the universe at an earlier stage of development. We see earlier generations of stars and galaxies and so forth. So we do see a difference. But those differences become really significant at length scales of more like 100 megaparsecs. And at any rate, they can be understood as a consequence of the fact that when we look out to those distance scales, we're observing the universe at an earlier stage of development. So the starting point for cosmology is the assumption that the universe is isotropic and homogeneous. Now, from the point of view of general relativity, these assumptions are really very rich and powerful. Notice that when we say the universe is isotropic and homogeneous, what we mean is that space is isotropic and homogeneous. So in other words, we're assuming that space-time can be split into slices, which are space at different times, and each one of these slices, these three-dimensional slices of space-time, is isotropic and homogeneous. So this is a diagram of space-time, and here we are. This is us now, and each of these slices is a three-dimensional space. So these are all isotropic and homogeneous. But these spaces don't have to be identical. So the space at the now time, so this is the now time, could be different from the space at some past time. So for example, the density on this past slice could be different from the density on this now slice. Now from a general relativity point of view, we have to ask what's special about these slices? Why not slice the space-time, say this way? And what's special about these slices is these slices are the slices in which the matter content of the universe is on average at rest. So let me erase these alternative slices and draw some world lines of matter. So here's our world line, here's another cluster of galaxies, another cluster of galaxies. So these clusters of galaxies are at rest with respect to these slices. In other words, the four velocity of any of these world lines is orthogonal to any of the basis vectors within three-dimensional space. And that must be true because if there were some velocity, if this cluster of galaxies had some velocity with respect to space as defined this way, then there would be a preferred direction at this point. But if we have a preferred direction, that breaks isotropy. Okay, we know that the universe is isotropic at this point because we know it's isotropic about us, and we're assuming it's homogeneous. So the universe must be isotropic about any point. So in particular, the cluster of galaxies here can't have any motion on average. So each of these world lines is at rest with respect to each of these spaces. And that's what defines this preferred slicing of space-time. It's the slicing such that the matter, which follows these world lines, is on average at rest. So our first task will be to determine how this structure restricts the space-time metric. And as usual in general relativity, our life will be easiest if we choose coordinates that are adapted to whatever structure we have. So let's use these slices to define constant values of a coordinate t. And we'll use spatial coordinates that are constant along these world lines. So let's denote the spatial coordinates as xi. So these remain constant along these world lines. So now these world lines are the integral curves of the vector field d by dt. And t itself we can choose to be proper time between the slices. After all, the proper time along this world line between these slices must be the same as this proper time, the same as this proper time, due to homogeneity. So we can use proper time as the label for these slices. So using these coordinates, the metric must have the following form. It's ds squared equals minus dt squared plus gij dxi dxj, where this part of the space-time metric is the spatial metric. It's the metric for a three-dimensional isotropic homogeneous space, and it in general is going to be t dependent. So it's going to change as the proper time t changes. Now the reason the GTT component of the metric is -1 is because if we look along a curve of constant spatial coordinates, if xi is constant, then ds squared is minus dt squared, or in other words, d tau squared is equal to dt squared. So this is just saying that t is to within an additive constant, just the proper time. and that's what we expect from the way we defined t. So this explains why GTT is -1. Now, next question, why is GTI equal to 0? And the answer is quite simple. If you recall, these world lines are orthogonal to the slices, so that means the basis vector d by dt is orthogonal to any of the basis vectors d by dxi that lie in the slices. So we have d by dt is orthogonal to any of the d by dxi's, but that is just GTI, the TI component of the metric. Now let's turn to this part of the metric, the spatial metric, and ask, what is a 3D isotropic homogeneous space? From a mathematical point of view, this is a maximally symmetric space. Which means it has the maximum possible number of killing vector fields. I should say the number of independent. And in 3 dimensions, that maximum number of killing vector fields is 6. Loosely speaking, 3 translations and 3 rotations. So let's see if we can deduce what the metric looks like. So let's pick a point in the 3-dimensional space, and let's send out geodesics from that point in every direction in all 3 dimensions. So these are all geodesics. And now let's measure along each geodesic out to 1 unit of proper distance. Let's say there's 1 unit of proper distance along each of these geodesics. And now we can connect all of these points to form a spherical shell. So this is in 3 dimensions, remember, and here's the spherical shell at a proper distance of 2 units away from our central point. So these are spherical shells. And they are in fact spheres. Each one has the geometry of a 2-dimensional sphere. And that's due to isotropy. We've traveled out along the geodesic along the same distance in each direction, and so the curvature of this shell must be the same in any direction. So since the curvature is constant all across this surface, it must be a sphere. So it's a 2D sphere, each one of these shells. Now on each one of these spherical shells we can introduce the usual spherical coordinates, theta and phi. And we'll also choose these spherical coordinates on each shell in such a way that they're lined up along the radial directions. So in other words, whatever the value of theta and phi is here, we'll use the same value here. And now let's choose a radial coordinate for our space, which is just the proper distance along the geodesics. Let's call it r. It's the proper distance along the geodesics. And of course, isotropy tells us that the proper distance between 2 spherical shells is the same along any of these radial directions. So now let's write down the metric for this isotropic homogeneous space using the coordinates r, theta, and phi. It's ds squared equals dr squared plus some function of r, which I'll call g of r, times d omega squared, where as usual d omega squared is shorthand for d theta squared plus sine squared theta, d phi squared. So it's the metric on a unit sphere. So why is the RR component of the metric equal to 1? Well, that's because we've chosen the coordinates such that R measures proper distance along the geodesics, which are curves of constant theta and phi. R is proper distance. And why are the off-diagonal terms, the R theta and R phi terms in the metric? So GR theta and GR phi equal to 0. Well, if you look at one of our spherical shells and one of our geodesics, so this is one of the geodesics, and this is a spherical shell, the geodesic must be orthogonal to the shell. In other words, the geodesic must point along the normal to the shell. If it didn't point along the normal to the shell, then there would be a preferred direction. That would violate isotropy. So the geodesic must be orthogonal to the shell, but the geodesics are integral curves of d by dr. The shell has basis vectors d by d theta and d by d phi, so these must be 0. The inner product of d by dr with either d by d theta or d by d phi. But this is just gr theta, and this is gr phi. So what we've now shown is the metric for a three-dimensional space that's isotropic and homogeneous must have this form. But actually, if you think about it, all we've used is isotropy about a single point. We haven't imposed that the space should be homogeneous yet. So we can impose homogeneity by demanding that the curvature is a constant at each point in the space. Now, by curvature here, I mean really any measure of curvature that's independent of any arbitrariness that the coordinates might introduce. So any geometrically defined measure of curvature. In other words, we need a curvature invariant. Now, the simplest curvature invariant is the curvature scalar. But that turns out to be a little bit of a messy choice. There's a simpler choice, and that is the RR component of the Ricci tensor. So the Ricci tensor is Rij, and we're going to look at the RR component. Now, normally when you look at a component of a tensor, you have to be concerned that that is a coordinate-dependent quantity. It depends on the way the coordinates have been defined. But remember, in our case, we've defined the R coordinate to be proper distance along a geodesic. So it's actually a geometric quantity. So the RR component is actually the type 02 tensor Rij acting on two copies of the vector field d by dr. And these vector fields are defined geometrically as proper distance along geodesics. So in particular, homogeneity tells us that this quantity should be the same at each point in the space. So homogeneity implies RRR is equal to a constant. Let's call that constant K. So now if we compute the Ricci tensor for this metric of this form, that just has this one unspecified function g of r, the RR component of the Ricci tensor is equal to g prime squared minus 2g times g double prime, where prime denotes differentiation with respect to r, divided by 2g squared, and that must equal some constant k. Now, just a little bit of playing around with this shows that the left-hand side can be written as minus 2 over the square root of g times the square root of g double prime. So that tells us that square root of g double prime is equal to minus 1/2 k times the square root of g. So we know how to solve this differential equation. For example, if k is positive, then the solution is just a simple harmonic oscillator. Square root of g is equal to some constant times sine of square root of k over 2 times r minus another constant, let's call that b. And if k is equal to 0, this just tells us that square root of g is equal to a linear function of r. Let's write it as a times r minus b. And finally, if k is negative, we have the solution square root of g is equal to, instead of sine, we have hyperbolic sine, sinh, and here we'll put the absolute value of k over 2 square rooted times r minus b. Now let me remind you the form of the metric we're dealing with. It's ds squared equals dr squared plus g of r times d omega squared. Now, in constructing these coordinates, we've introduced a coordinate singularity at r equals 0, where the radial geodesics converge. So we need to be careful about the point r equals 0. And one thing we know about that point is, just like any geometry, it should be smooth at r equals 0, and if we look in a close enough region, it should be approximately flat near r equals 0. So that tells us that close to r equals 0, the geometry, the metric should look like dr squared plus r squared d omega squared. So in particular, the square root of g should be approximately equal to r near r equals 0. Now if we look at these expressions for square root of g, you'll see that this will be true if, in this case, b is equal to 0 and a is equal to square root of 2 over k. In this case, we need b equals 0 and a equals 1. And in this case, we need b equals 0 and a equals square root of 2 over absolute value of k. So with these values for the constants a and b, the metric for the isotropic homogeneous space ds squared equals dr squared plus 2 over k times sine squared of the square root of k over 2 times r d omega squared. This is the case k greater than 0. For k equal to 0, we have dr squared plus r squared d omega squared. And finally, for k less than 0, we have dr squared plus 2 over absolute value of k times hyperbolic sine squared of the square root of absolute value of k over 2 times r d omega squared. So each of these three metrics represents a homogeneous isotropic space, and of course this k equals 0 case is just flat space. The case with positive k is actually a three-dimensional sphere, and this k less than 0 case is a three-dimensional hyperboloid. Let's take a closer look at that. Let's start with this k positive case. So when k is greater than 0, this is a three-dimensional sphere of radius square root of 2 over k. To see this, let's change coordinates. Let chi equals square root of k over 2 times r, then d chi is square root of k over 2 times dr, and it's easy to see then the metric becomes 2 over k times d chi squared plus 2 over k times sine squared of chi d omega squared. And now let's make a slight change of notation. Let's let the radius of this three-sphere, call it a. Then the metric becomes a squared times d chi squared plus sine squared chi, and then d omega squared is, of course, d theta squared plus sine squared theta d phi squared. And now you can show that this metric is a three-dimensional sphere by considering a flat four-dimensional space. So this is not physical. This has nothing to do with physics. It's just mathematics. Consider the space described by the flat metric in 4 dimensions, dx squared plus dy squared plus dz squared plus, let's say, dw squared. And now define a surface in this space by x equals a sine chi sine theta cosine phi, y equals a sine chi sine theta sine phi, z equals a sine chi cosine theta, and w equals a cosine chi. Now if you use this flat metric to define the geometry of this surface, you find precisely this metric. And furthermore, this surface satisfies x squared plus y squared plus z squared plus w squared equals a squared, which means it's a three-dimensional sphere of radius a. So the three-dimensional isotropic homogeneous space with k positive is a three-dimensional sphere. The case with k negative is a three-dimensional hyperboloid, and we can show that in much the same way. So let's consider k less than 0 case. This is a 3D hyperboloid with radius, or what we'll call radius, square root of 2 over k over absolute value of k. To see this, we make a change of variables. We let chi equal square root of absolute value of k over 2 times r, and we'll also define this radius as little a, and then the metric, it's not hard to see, becomes a squared times d chi squared plus hyperbolic sine squared of chi times d omega squared, that's d theta squared plus sine squared theta d phi squared. And now to show that this is a hyperboloid, we define a four-dimensional flat space-time, an unphysical space-time, by minus dt squared plus dx squared plus dy squared plus dz squared. And then we consider the surface in this space-time, defined by x equals a times hyperbolic sine of chi times sine theta cosine phi, y equals a hyperbolic sine chi sine theta sine phi, z is a hyperbolic sine chi cosine theta, and t is a times hyperbolic cosine of chi. So when you plug this surface into this line element, you find this metric precisely. And furthermore, this surface satisfies t squared minus x squared minus y squared minus z squared equals a squared. And this is a hyperboloid. We could draw it if we suppress one of the dimensions, say the z direction. So this is the x-axis, y-axis, and the t-axis. On this diagram, the surface looks like a bowl. But remember, this surface is not a surface in Euclidean space, it's a surface in Minkowski space-time. So now let me summarize our results for the three-dimensional isotropic homogeneous spaces. We have three cases. First, the sphere, the case of a three-dimensional sphere, the line element is a squared times d chi squared plus sine squared chi d omega squared. And that's the k greater than 0 case. And for the k less than 0 case, we have a squared times d chi squared plus hyperbolic sine squared of chi times d omega squared. And for the k equals 0 case, you'll recall the metric is just the flat metric, dr squared plus r squared d omega squared. And we can write this in a way that looks similar to these line elements by making a change of variables. R equals a times chi for some constant a. And then the metric in this case becomes a squared times d chi squared plus chi squared d omega squared. Now let's recall the meaning of this constant k. K was the RR component of the Ricci tensor, where we were using coordinates in which r measured proper distance along radial geodesics. And for these three metrics, it turns out that this is proportional to the curvature scalar. We could write the curvature scalar in terms of k, but notice that we replaced k in these line elements with this new parameter a, so it's more convenient to write the curvature scalar in terms of a. So when we do that for the k greater than 0 case, we find the curvature scalar is equal to 2 divided by a squared, which is positive. The curvature scalar for the k equals 0 case is, of course, r equals 0. This is just flat space. And the curvature scalar for the k less than 0 case is negative 2 over a squared. So these three cases of three-dimensional isotropic homogeneous spaces are characterized by their scalar curvature being positive, 0, or negative. Now, the coordinates used in writing these three metrics have the advantage of being closely tied to the symmetries of these spaces. But there's another set of coordinates that are very convenient for use in cosmology. And those coordinates are defined by replacing chi with a new coordinate r, which is defined as sine chi for the r positive case. It's just chi for the r equals 0 case, and hyperbolic sine of chi for the r negative case. Now this new coordinate r is not the same as the coordinate r that I used earlier in the lecture. So this is a new definition of r. And when we make this coordinate transformation, it's easy to see that the metric becomes a squared times dr squared over 1 minus r squared plus r squared d omega squared for the scalar curvature positive case. For scalar curvature equal to 0, we just have a squared times dr squared plus r squared d omega squared. And for the scalar curvature negative case, we have a squared times dr squared over 1 plus r squared d omega squared. Now these three line elements can be written all together if we introduce a new parameter that's usually called k. Now this is a new definition of k. It's not the same constant that I called k before. And this is defined as the sine of the scalar curvature. So it's k, this k is equal to plus 1 in this case, minus 1 in this case, and 0 in this case. So it's either plus or minus 1 or 0. And this is a new definition of k. Although it is true that the sign of r is the same as the sign of the old k, so our new k is the sign of the old k. But with this definition, we can now write the metric as a squared times dr squared divided by 1 minus k times r squared plus r squared d omega squared. And this accounts for all three cases. When k is equal to plus 1, that's the positive curvature case. If k is equal to 0, that's the flat case. And k equals minus 1 corresponds to the negative curvature case. And now we're finally ready to put all this together and write down the space-time metric. Recall we showed that the space-time metric has the form minus dt squared plus the metric for a homogeneous isotropic space. That's of course what we have written here. But remember, this is in general t-dependent. So space-time can be viewed as a stack of slices. Each one of these slices is a three-dimensional isotropic homogeneous space, but they don't have to all be the same isotropic homogeneous space. So space can evolve in time t. Now if you look at this line element for an isotropic homogeneous space, you see that it depends on two quantities, a continuous parameter a and a discrete parameter k. So this continuous parameter a could change and evolve with t, so it can depend on t. On the other hand, this discrete parameter k can't change because if it's, for example, if it's equal to 1 on one slice, it can't suddenly jump to equal minus 1 on the next slice. That would be a discontinuity in the space-time metric. So k is fixed in the space-time metric, but a is a function of t. So the space-time metric has the form ds squared equals minus dt squared plus a of t squared times dr squared over 1 minus k times r squared plus r squared d omega squared. And this is referred to as the Robertson-Walker metric. Or the Robertson-Walker spacetime, or the Robertson-Walker cosmology. And there are three cases. The case with k equal plus 1, where space has the geometry of a three-dimensional sphere. This is often referred to as a closed cosmology. The case k equals 0, space has a flat geometry. This is often referred to as a flat cosmology. And the case k equal minus 1, where space is a hyperboloid. And this is often referred to as an open cosmology. The term closed comes from the fact that a sphere is a closed geometry. It has a finite volume. Open refers to the fact that a hyperboloid is an open geometry. It extends to infinity in all directions and has infinite volume. I think it's useful at this point to pause and consider how far we've come. The only input to our analysis so far is that the universe is isotropic and homogeneous, and from those assumptions alone we're able to deduce that the metric has this very limited form. Notice that the only freedom here in the Robertson-Walker metric is a single function of a single coordinate, this a of t, along with this parameter k that can only take three values, plus or minus 1 or 0. So considering that the metric in general is 10 functions of 4 variables, of 4 coordinates, this is quite a significant restriction on the form of the metric. At this point you might be wondering, how do we determine this function a of t, which by the way is referred to as the scale factor, and the parameter k? How are they determined? And they're determined when we impose the Einstein equation. And in turn, the Einstein equation depends on our choice for the matter content in the universe. I plan to go through that analysis in detail in the next lecture, but for now I just want to focus on some of the properties of this Robertson-Walker metric. Let me begin by drawing a TR diagram, where T and R are the Robertson-Walker time and radial coordinates. So this is the R axis, this is the T axis, and we'll place ourselves, our own cluster of galaxies, at the origin at R equals 0. We can place it anywhere we like because of homogeneity, but we'll just choose ourselves to be at R equals 0. So here's our world line. This is us, and this is a world line of some distant cluster of galaxies. And remember, all of the matter on average is at rest in these space-like slices, these isotropic homogeneous spaces. And the world lines are at constant values of the Robertson-Walker spatial coordinates, so constant r, theta, and phi. So this is r equals 0, and this is r equals some constant value, let's call it big R, not to be confused with the curvature scalar. And what I'd like to do now is compute the proper distance between us and this distant cluster of galaxies. So we'll call this distance d, and this distance will change in time, so it's a function of time. So let me write down the Robertson-Walker metric for reference. It's ds squared equals minus dt squared plus a of t squared times the quantity dr squared over 1 minus k times r squared plus r squared d omega squared. Now this distance is being computed along a constant angular direction, so theta equal constant and phi equal constant. So in the line element, d omega squared is 0, and we're also computing this distance along a t equal constant surface. So dt is 0. So the proper distance squared is just equal to a of t squared times dr squared divided by 1 minus kr squared. And from this we find, of course, ds is equal to a times, that's a of t, times dr divided by the square root of 1 minus kr squared. Now we can integrate both sides. The left side is just what we're calling the total distance, d of t, and on the right side let's pull out this factor of a of t since it's independent of the coordinate little r. So it's a of t times the integral from 0 to big R of dr divided by the square root of 1 minus kr squared. Now this factor, this integral, just depends on capital R. In other words, it depends on which cluster of galaxies we're looking at, and it depends on this parameter little k, but it's just a constant. In particular, it's a constant in t. It doesn't depend on t. So we see here that the total distance is proportional to this scale factor a. So for example, if the scale factor is increasing in time, then the proper distance between clusters of galaxies increases with time. And now we can take this relation that says d of t is equal to a of t times a constant and differentiate this with respect to time. Let's use dot for the derivative. So we have d dot is equal to a dot times the same constant. Now we can divide these two equations to obtain the following result. We have d dot is equal to a dot divided by a times d. This combination a dot over a appears a lot in cosmology, so we give it a special symbol h, and h depends on time t because a depends on t. So h is defined as a dot of t divided by a of t. And this is the Hubble constant, or the Hubble parameter. Sometimes called the Hubble constant. Of course, it's not constant, it depends on t, but it is a constant in the sense that it's independent of the spatial coordinates. It's the same value everywhere in space, so it's a spatial constant. We can now write this result for the proper distance between clusters of galaxies as d dot equals h of t times d. So the rate of separation, d dot, is proportional to d, the separation, So if we double the separation, then we double the relative velocity. And the proportionality between distance and velocity is the Hubble parameter h. Now the current value of the Hubble parameter sometimes called h naught. This is h at time t0, where we often use the notation t0 to denote the current time. This is approximately 70 kilometers per second per megaparsec. So two clusters of galaxies that are separated by a megaparsec are receding from each other at about 70 kilometers per second. Now this number, which comes from observations of our universe at the present time, it's positive, which tells us that A dot is positive. So the scale factor is increasing in time, so the universe is expanding. Now let's consider a graph of the scale factor as a function of t. So along the horizontal axis is the t-axis, and vertically I'll plot A of t. And we haven't really talked about what A of t looks like yet. That's for the Einstein equation to determine. But let's say it looks something like this. And this is t naught, so it's now, it's the present time. If you look at the slope of this graph at this point, this slope is A dot at the present time, t naught. And now let's form a little triangle here. This is the distance A at the present time, t naught. And this interval we refer to as t sub h, which is called the Hubble time. And now you see from this diagram that the slope at the present time can be written as the scale factor at the present time divided by the Hubble time. So this tells us that t sub h is the present value of the scale factor divided by A dot at the present time. But this is just the inverse of the Hubble parameter at the present time. So we have t sub h is equal to 1 over h0, the present value of the Hubble parameter. And you can see from this graph that t sub h is the time that the scale factor would go to 0 if we assume the scale factor has a constant slope, constant equal to the present value of A dot. So the Hubble time is the age of the universe, assuming A dot is approximately constant, equal to the present value. Of course, A dot will not turn out to be a constant, so t sub h is only an approximation to the age of the universe, but nevertheless, t sub h is approximately 14 billion years. When we observe the universe, we observe distant clusters of galaxies. We don't see those galaxies at the present cosmological time. Instead, what we observe is the light that was emitted from those galaxies in the distant past. That light travels along null geodesics and is just now reaching our location. So let me once again draw a TR diagram. This is the R-axis, this is the T-axis, and we'll place ourselves at the origin, R equals 0, so this is our world line for our cluster of galaxies. So this is us at R equals 0, and here's some distant cluster of galaxies. At some coordinate value, say capital R. And when we observe this distant cluster of galaxies, we observe the light that's been emitted from the past, and this light travels along a null geodesic. So this light was emitted at some earlier cosmological time. Let's call that t sub e for the time emitted. And the time observed is the present time, t sub 0. Now the Robertson-Walker metric is ds squared equals minus dt squared plus a of t squared times dr squared over 1 minus k r squared plus r squared d omega squared. And for a null geodesic, ds squared is 0, so 0 equals minus dt squared plus a of t squared dr squared divided by 1 minus k r squared. And because we placed ourselves at the origin of coordinates, this null geodesic is along a radial direction, so d omega squared is 0. So from here we find dt over a of t equals dr divided by 1 minus kr squared. And we can integrate both sides. So this is integral from te to to, the emission time to the observation time. And this is integral from 0 to capital R. Actually, this should be the square root of 1 minus kr squared in the denominator. So now let's consider a second null ray that's emitted just after this first one was emitted. So here's a second null ray that's emitted at some time. Let's call the emission time Te plus delta Te. And the observation time then is To plus delta To. So we can do the same calculation for this second null ray. And of course what we'll find is a similar result, but with Te replaced by Te plus delta Te, and To replaced by To plus delta To. And on the right-hand side, we'll have the same integral from 0 to r, dr divided by the square root of 1 minus kr squared. And now let's subtract this first equation from the second equation. And of course, the right-hand sides cancel. And what we're left with is the integral from Te plus delta Te to Te plus the integral from To 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 plus delta To equals 0. Or in other words, integral from Te to Te plus delta Te is equal to the integral from To 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 plus delta To. And now if we take the limit as delta Te and delta To become infinitesimally small, the integral on the left just becomes delta Te divided by a of Te, and the integral on the right is delta To divided by a of To. Now let's imagine that these two null geodesics are the world lines of successive peaks of an electromagnetic wave. Then delta Te is the period of the wave as viewed when it's emitted, and delta To is the period of the wave as it's observed. And so this is equal to 1 over the frequency of the emitted wave, and this is 1 over the frequency of the observed wave. So this equation becomes 1 over the emission frequency times the scale factor at the time of emission equals 1 over the observed frequency times the scale factor at the time of observation. So here I'm defining AE as A at the emission time and AO as A at the present time. So from here we have the observed frequency divided by the emitted frequency is equal to AE over AO, or equivalently, if we remember that frequency is 1 over wavelength, This tells us the observed wavelength divided by the emitted wavelength is AO divided by AE. And this just describes the cosmological redshift. So we have, since the universe is expanding, AO is larger than AE. So that tells us that the observed wavelength is larger than the emitted wavelength, or equivalently, the observed frequency is less than the emitted frequency. Now, the cosmological redshift is commonly used as a distance measure in cosmology because it's so closely tied with observations. So we define what's often called the redshift z as a distance measure. So z is defined as the change in wavelength divided by the emitted wavelength. So that's lambda O minus lambda E divided by lambda E. Or in other words, lambda O divided by lambda E minus 1. And from this result, we have lambda O divided by lambda E is just AO divided by AE. So there are lots of different measures of distance that are introduced in cosmology. Besides the redshift distance, we have things like the luminosity distance, and these are measures that are closely tied to observations that we can actually make. And of course, the reason we do this is because we can't directly observe the distance between us and some other cluster of galaxies at a single cosmological time. So this is us. This is another cluster of galaxies. This is the present cosmological time, T0. The distance, the proper distance between us and this cluster, we'll call it D0. We can't measure directly. We can only observe photons that were emitted at a past cosmological time, TE. Now, the relationship between these different measures of distance can be worked out in detail with a little effort. For example, we can relate the redshift distance z to the proper distance d0. This is a very rough calculation. So we write z this way. This is a0 minus ae divided by ae. And if we assume that this cluster of galaxies is fairly close, so the scale factor a hasn't changed very much, then this is approximately a0 minus ae is approximately a0 dot times this time interval delta t. That's this time interval to minus te. And the denominator is, since a hasn't changed very much, we can just call this a0. So this is a0 dot over a0, which is the present value of the Hubble parameter, times delta t. But delta t, again, if this is cluster of galaxies is close, and we just assume this is approximately flat space-time, then delta t is approximately d0. So this is h0 d0. And now turning this around, we can write the proper distance as approximately 1 over the present value of the Hubble constant times z. Now a more careful analysis shows that this is just the leading order term in a series expansion that looks like z plus 1/2 h naught dot, that's the time derivative of the Hubble parameter at the present time, divided by h naught 0 times z squared, and so forth. If you're interested in how this calculation is done, I'll include it along with some guidance as one of the practice problems.